Welcome to the SWAYAM NPTEL course on food microbiology for safe and sustainable food systems. In the last lectures, we have been discussing the thermal processing of foods, and in the last lecture, we have discussed the thermal death rate kinetics. And now, we will be discussing irradiation, and we will be discussing introduction, ionizing radiations, gamma rays, UV radiation, microwaves, and adverse effect of food irradiation. Irradiation as a method for food preservation has been studied for more than 50 years. In this process, food is treated to a specific dosage of ionizing radiation for a specified period of time. This process has several food applications such as slows or delay spoilage due to the growth of pathogens, inhibition of sprout, delay in fruit ripening, increase of juice yield, and improvement of rehydration. In the process of food irradiation, it targets organisms' DNA beyond its ability to repair, and organisms can no longer able to continue to process of cell division. Hence, the target organism ceases all processes related to metabolic reproduction. It is believed that irradiated food does not become radioactive because the particles that transmit radiation are not themselves radioactive. Although still there is some controversy in the application of ionizing radiation, as it produces a higher energy transfer per collision than conventional radiant heat. Recently, food irradiation is allowed by over 50 countries, where about 5 lakhs metric tons food is treated annually. In general, radiation may be defined as the emission and propagation of energy through space or through a material medium. Electromagnetic type of radiation is of primary interest in food preservation. This is the pictorial representation of electromagnetic waves which are of different types, like for example, depending upon the wavelength or frequency, the wavelength of radio frequency rays is more. Like this is the pictorial representation of different types of rays. Depending upon the wavelength and the frequency, you can say the radio waves, they are having the maximum wavelength and has got the penetration power to the atmosphere, Earth's atmosphere. And just for the layman's understanding, the approximate scale of wavelength is given are represented by the height of a building, that is the more. Likewise, for microwaves, it is 10 to the power minus 2, and it is represented like the human's heights. Likewise, it is the just for the layman people, it is represented in this fashion. Otherwise, for the wavelength wise, the wavelength of infrared lights is further less, and visible light it is further less. Likewise, it is goes on decreasing up to the gamma rays, which is 10 to the power minus 12. And when the wavelength is decreasing, then we can see that the frequency is increasing, and the temperature relation is also given at which these radiations are emitted. The electromagnetic spectrum may be divided into two categories, one of each side of visible light from radio waves to infrared, low frequency, long wavelength and low quantum energy radiations related to thermal agitation of the food. Other side of the visible light, from ultraviolet to gamma rays, the high frequency, shorter wavelength and high quantum energy radiations. Such types of radiations actually excite and degrade the organic compounds and microbial cells without heating of the food product. Destruction of microorganisms without considerably increasing temperature, and the process is called cold sterilization. The food technologist classified radiations of interest in food preservation on the basis of their wavelengths, the shorter wavelengths being the most injuring to microbes. This spectrum may be further divided into three types with respect to these radiations. First, ionizing radiations, then ultraviolet rays, then microwaves. Ionizing radiation. Ionizing radiations are of primary interest in food preservation. These radiations have wavelength of 200 Armstrong or less. For example, alpha particles, beta rays, gamma rays, X rays and cosmic rays. Their quanta contain enough energy to ionize molecules in their paths. Ionizing radiation is applied to foods to improve their keeping quality. Foods processed with ionizing radiation are known as irradiated. They are not radioactive, and such radiations destroy microorganisms without appreciably raising temperature. Hence, the process is called cold sterilization. The microbial cells are affected directly and indirectly by ionizing radiations. Indirect effect, because these radiations interacting with key molecules, that is the chromosomes, with hydroxyl radicals cause single and double strand breaks in the DNA molecule, resulted in removal of hydrogen from deoxyribose sugar within the cell. Indirect effect, the generation of free radicals by the radiolysis of water, and further free radicals can combine with oxygen molecules to give powerful oxidizing agents that can damage cell components. Therefore, food without water and oxygen requires higher radiation doses, that is up to 2 to 3 times, to obtain the same lethality of food with sufficient water and oxygen. This is the pictorial representation of how ionizing radiations they work. In the direct damage, they actually cause the double strand break or the single strand break, and which causes ultimately the cell death, whereas in indirect damage they actually produce free radicals and reactive oxygen species like this, and they then break the double strand break or the single strand break, and in that process the cell death occurs. Now, gamma rays. Gamma rays playing a very important role in food preservation, because it is the cheapest form of radiation, and the source elements are either byproducts of atomic fission or atomic waste products. Gamma rays have excellent penetration power similar to UV rays, making it potentially an ideal method of food preservation. Hence, gamma rays can be used to kill or destroy contaminating microorganisms in packaged food. Such type of electromagnetic radiations emitted from the excited molecules of elements, that is 60 that cobalt and 137 cesium. In addition to above, 60 cobalt has a half-life of about 5 years and the half-life for 137 cesium is about 30 years. Successful irradiation of foods by using gamma rays may be achieved by the following three ways. Radapultization is equal to radiation sterilization or commercial sterility that destroys all forms of microorganisms. This process is suitable to only few food products, that is bacon, because as the high doses of radiation up to 50 kilo Gray may cause color changes and or production of off odors. Radicidation. It is equivalent to pasteurization of milk, where reduction of the number of viable specific non-spore forming bacterial pathogens achieved. Irradiation levels of 5 kilo Gray or below are effective in destroying non-spore forming and non-viral pathogens. This process may be used to preserve the foods such as fresh poultry, red fish, spices and condiments. Now, radiurization. In this process, low levels of radiations applied to improve the keeping quality of a food by causing substantial reduction in the numbers of viable spoilage microorganisms, especially gram-negative non-spore forming rods. Dose of radiation below 2.5 kilo Gray is sufficient to increase the shelf life from 2 to 6 folds of fresh meats, poultry, seafood, fruits, cereal grains and vegetables. Now, UV radiation. Ultraviolet light is considered powerful bactericidal agent and with the most effective wavelength being about 260 nanometer. It is non-ionizing type radiation. Microbial proteins and nucleic acids showed maximum absorbance. In general, UV light is absorbed by purine and a pyrimidine base leads to the formation of covalent bonds between adjacent thymine molecules resulted in thymine dimers. These may interfere the process of DNA replication as well as disrupt normal gene functioning, which creating new mutants. Naturally, microorganisms have the capacity to repair this DNA damage, but extensive damage may cross the limits of DNA repair mechanisms, leading to cell death. Microbial resistance to UV light is largely determined by their ability to repair such type of damages. Besides these repair mechanisms, few microbes also synthesize some protective pigments, like for example Micrococcus luteus produces yellow water insoluble pigments. In general, sensitivity to UV irradiation follows the pattern. The gram-negative are the most susceptible, followed by gram positive, followed by yeast, followed by bacterial spores, followed by mold spores, followed by viruses. Viruses are the least susceptible to the UV light. Ultraviolet radiation of high intensity can be generated by low pressure mercury vapor lamps, is considered extremely effective in killing microorganisms. Penetration capacity of many radiation playing very important role in food application, as UV light has the poor penetrating capacity restricts its use. It can able to penetrate only to 3 to 5 meter in air, 0.3 meter in water and less than 0.001 meter glass and milk. Hence, the applications of UV light are limited to surface disinfections and air sterilization, surface sterilization of wrappers and packaging rooms in food and pharmaceutical industry. These are the mechanism of photocatalytic interaction of bacteria and viruses. This shows the bacteria, how it acts on the bacteria, and this figure shows on the viruses how it works on the pathogens. So, for the bacteria, let us discuss first the reactive oxygen species, namely hydroxyl radicals and superoxide ions generated after UV irradiation first damage the cell wall layers, thus allowing the leakage of small molecules such as ions. The reactive oxygen species can thus further penetrate the cell such that the degradation of internal components may occur, followed by complete mineralization. The degradation process may occur progressively from the side of the wall in contact with the catalyst, and ultimately this results in the cell death. Whereas in the case of viruses, the hydroxyl and the superoxide anion generated are able to degrade the capsid and envelope of proteins and phospholipids of non-enveloped and enveloped viruses respectively. Besides, the leakage and consequent nucleic acid degradation occurs, ultimately leading to the inactivation of the viral particles. Microwaves in the electromagnetic spectrum occupy frequencies between the infrared, that is 10 to the power 9 hertz, and radio frequency, that is 10 to the power 12 hertz, has comparatively low quantum energy. Microwaves are generated using a device first developed in the United Kingdom during research into radar during the Second World War called magnetron. For most food research, mainly two frequencies, 915 megahertz and 2450 megahertz are used. Microwaves act indirectly on microorganisms through the generation of heat. In microwave oven, when electrically neutral foods are placed in an electromagnetic field and the charged symmetric molecules are driven first one way and then another. In this process, each asymmetric molecule attempts to align itself with the speedily changing alternating current field and the molecules oscillate about their axis while attempting to go to the proper positive and negative poles. Intermolecular friction is developed with apparent heating effect. This temperature effect is accountable for killing microorganisms in food. Microwave radiations are used both commercially and domestically in domestic microwave ovens and in catering to defrost frozen meats before cutting. In blanching of vegetables and fruits, destruction of molds in bread, pasteurization of beer and sterilization of wine, etc. The irradiation level and examples of irradiated foods. The irradiation level, that is the low dose, which is less than or equal to 1 kilo Gray, that is actually used for the sprouting inhibition, and the doses of the level of 0.06 to 2.2 kilo Gray, and the examples are potatoes, onions, garlic, ginger, chestnuts, etc. It can also be used for the disinfections of insects, and the dosage levels are between 0.15 to 1 kilo Gray, and the examples are cereals and legumes, fresh including quarantine treatment and dried fruits, dried fish and meat, etc. It can also be used for parasite disinfection, and the dosage used are 0.3 to 1 kilo Gray, and the examples of food is fresh pork, freshwater fish, fresh fruits. It can also be used for delaying of ripening in the dose level of 0.5 to 1 kilo Gray for fresh fruits. This medium doses, that is in the range of 1 to 10 kilo Gray, can be used for radiolization and radicidation of foods. For extension of shelf life, the dose level is between 1 to 3 kilo Gray. For raw fish and seafood, fruits and vegetables, it can be used for the removal and inactivation of spoilage microorganisms, where the dose level varies from 1 to 7 kilo Gray, and the examples of food are raw and frozen seafood, pathogenic bacteria of meat and poultry, spices and dried vegetables, seasonings, etc. It can also be used for improving technical parameters in the dose level of 3 to 7 kilo Gray, for example, increasing juice yield, properties of foods, especially from the grapes, reducing cooking time of the dehydrated vegetables. And in the high doses, that is more than 10 kilo Gray, it can be used for the reapertization of foods, for industrial sterilization in the dose level of 30 to 50 kilo Gray, for meat, poultry, seafood, in combination with mild heat, sausages, prepared meals, hospital diets, decontamination of certain virus, enzyme inactivation, etc. The high doses in the range of 10 to 50 kilo Gray can be used as a food additives and ingredients in case of spices, enzyme preparations and natural gum gel, etc. The effect of irradiation on food. Some foods such as dairy foods and eggs cannot be irradiated because it causes changes in flavor or texture. Fruits, vegetables, grain foods, spices and meats such as chicken can be irradiated. Irradiation causes minimal changes to the chemical composition of the food. However, it can alter the nutrient content of some foods. because it reduces the level of some of the B group vitamins. This loss is similar to those that occur when food is cooked or preserved in more traditional and accepted ways such as canning or blanching. The FDA has approved a variety of foods for irradiation in the United States, which include beef and pork, crustaceans, for example lobster, shrimp and crabs, fresh fruits and vegetables, lettuce and spinach, poultry, seeds for sprouting, for example for alfalfa sprouts, shell eggs, shellfish like molluscan, for example oysters, clams, mussels and scallops, spices and seasonings. Now, adverse effect of food irradiation. Though food's irradiation is beneficial up to certain extent in food preservation and can replace chemical hazards to health, but the following adverse effects are also noted because not all foods are suitable for irradiation treatment. Food loses its nutritive values because of the destruction of the vitamins and nutrient content in foods, and few protein foods are flavor sensitive to radiation and may develop off flavors. Sometimes softening and discoloration may occur in some fruits, and milk may acquire an unpleasant taste. Blocking of the degradation processes of microbial and enzymatic during irradiation process makes food fresher than it actually is, and food looks like fresh food, but actually it is not fresh and may have lost much of its nutritional components. Such type of changes mislead the consumer because it is tough to differentiate the natural fruit to treated fruit. It is believed that food irradiation leads to the production of free radicals and highly reactive products which react by forming products of radiolysis, uncertain and sometimes causing deterioration of the organoleptic qualities of food. This is a possibility of the adverse reaction of radiolysis products on human health, which cannot be ignored, though these types of effects are not yet reported. Irradiation processing of food is its low level of acceptance by the consumers because of a perceived association with radioactivity. In the process of food irradiation, we use nuclear technology, which is greatly concerned with our environment, and hence it raises all environmental issues relating to the application of such type of technologies. According to the Codex standard for the labeling of pre-packaged foods, that is Codex Stan 1-1985, it is mandatory to inform consumers about irradiated foods and requires that the level of any food that has been treated by ionizing radiation or containing irradiated ingredients must bear a statement to that effect. And this is the pictorial diagram which should be mentioned on the label of the packaged food. The physical preservation methods are mostly aimed at prolonging the durability of foods by slowing down or repressing the spoilage mechanism by the alteration of relevant parameters. Irradiation as a method for food preservation has been studied for more than 50 years. In this process, food is treated to a specific dosage of ionizing radiation for a specified period of time. Radiation processing of food offers several food applications such as slows or delay spoilage due to the growth of pathogens, inhibition of sprout and delay in fruit ripening, increase of juice yield, improvement of rehydration, post-harvest losses of food and increasing availability to mankind.